Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore the 5 deepest points of the oceans. The most obvious and well-known one, we already know, the Mariana Trench. But what about the other 4? If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. The pressure at the bottom of the Mariana Trench is 1,086 bar, approximately 1,071 times the atmospheric pressure at sea level, or 8 tons per square inch. The temperature at the bottom ranges from 1 degree Celsius to 4 degrees Celsius. The Challenger Deep, the deepest point of the trench, is located about 322 kilometers southwest of Guam in the western Pacific. The trench is crescent-shaped and measures about 2,550 kilometers long and 69 kilometers wide. Only a handful of people have made it down there. Swiss explorer Jacques Piccard and American Don Walsh reached the bottom in January 1960 aboard the Bathyscaphe Trieste. Filmmaker James Cameron did it again in 2012. In 2019, Victor Vescovo found a plastic bag and candy wrappers at the bottom. Imagine stacking Mount Everest, the tallest mountain on Earth, at 8,849 meters, and then sinking another 2,100 meters past its summit. That extra stretch still wouldn't reach the bottom of the Mariana Trench. The abyss swallows structures that the human mind can barely wrap itself around. For anyone who's never dived more than a few meters in a pool, the idea of 11 kilometers of water column above your head stays abstract, until you put it in terms of pressure. 8 tons per square centimeter, crushing every exposed surface. At Challenger Deep, the pressure exceeds 1,086 bar, more than 1,000 times the pressure at sea level, in total darkness and temperatures between 1 and 4 degrees Celsius. That colossal pressure is no geographic accident. The Mariana Trench is the geomorphological result of a subduction zone, located at the convergent boundary between the Pacific and Philippine tectonic plates. When 2 plates collide, the denser one dives beneath the other in a slow, continuous process. That dive gradually carves out the ocean floor, building up depth over millions of years. At the southern end of the trench, Challenger Deep is deeper than the rest for a specific reason. The subducting portion of the plate is thought to have broken apart, lost lateral support, and begun sinking in a much more vertical path. The effect is straightforward. The abrupt plunge concentrates the greatest depth at a single point. Getting there requires extreme engineering. Walsh and Piccard descended on January 23, 1960, aboard the Bathyscaphe Trieste, a 15-meter-long vessel with a buoyancy control system using lead weights. The two spent 9 hours inside a compartment not much bigger than a refrigerator. Think about that, a refrigerator wrapped in thick metal walls, 11 kilometers above the ocean floor. Any crack in the hull, any seal failure, and the external pressure would destroy the submersible in a fraction of a second. There's no room for improvisation in that environment. Half a century later, technology had advanced, but the risks remained. In 2012, James Cameron made a solo descent in the Deep-Sea Challenger, spending about 3 hours piloting what was described as the first crewed scientific exploration of his submarine, reaching a depth of 10,898 meters. The ascent took 70 minutes. Cameron had planned to stay up to 6 hours collecting samples, but the mission was cut short by technical problems. Even so, the footage and data gathered during that and other expeditions revealed something that went against decades of scientific skepticism. The Mariana Trench is home to a surprising diversity of organisms. Mariana snailfish, xenophyophores, unusually large amphipods, the so-called Dumbo octopus, and a variety of bacteria and archaea. These creatures don't just survive, they thrive. Their bodies have developed precise adaptations, flexible, fluid-rich structures instead of rigid, air-filled skeletons, which allows them to balance their internal pressure with the crushing external environment. In the absence of sunlight, they navigate using sensory systems that detect vibrations in the water and feed on organic matter that slowly sinks from the surface. In 2005, researchers discovered that tiny single-celled organisms called foraminifera, a type of plankton, live in Challenger Deep. Without sunlight, these creatures benefit from nutrient-rich waters released by hydrothermal vents and mud volcanoes in the area. Hydrothermal vents at the bottom of the Mariana Trench expel superheated water and dissolved minerals that sustain entire ecosystems independent of solar energy. It's like discovering a city running without electricity, powered by something else entirely. The exploration of this abyss also revealed something unsettling about humanity's footprint on the planet. One of the finds from Vescovo's expedition was a plastic bag full of candy wrappers at the bottom of the ocean. Waste produced at the surface gradually sinks, traveling kilometers through the water column before settling in the most remote and inaccessible place on Earth. Synthetic materials that didn't exist 100 years ago have already reached depths that humans have only visited 3 times in history. The extent of that reach defies any intuition. Humanity has better maps of the surfaces of the Moon and Mars than of the depths of its own planet. According to NOAA, only 20% of the ocean floor has been mapped to date. The Mariana Trench specifically has been visited by fewer people than have walked on the Moon. Ironically, orbiting Earth at 400 kilometers of altitude, something dozens of astronauts have done, demands less extreme technology than descending 11 kilometers below the ocean surface. The pressure of space is 0. The pressure of the abyss is 1,000 atmospheres. Each expedition to Challenger Deep adds layers to what science thought it knew about the limits of life and matter. Organisms that should be crushed thrive. Geological structures continue their imperceptible movement, deepening the abyss millimeter by millimeter over vast stretches of time. The pressure that would destroy any submarine not specifically designed for that environment is the same pressure that sustains unique ecosystems, shaped creatures with no equivalent at the surface, and continually challenges humanity's ability to reach the limits of its own planet. An abyss that has existed far longer than we will be around to study it. The Tonga Trench sits in the southwestern Pacific, off the coasts of Tonga and Fiji, and its deepest point, the Horizon Deep, is the lowest point in the entire southern hemisphere. The Horizon Deep reaches 10,823 meters in depth. The trench is the site of the fastest subduction on the planet. The convergence rate has been estimated at 15 centimeters per year, but GPS measurements indicate up to 24 centimeters per year in the northern section of the trench, roughly the width of a finger per year, building up energy that gets released as earthquakes and tsunamis. The crust along one section of the trench is disappearing faster than anywhere else on Earth, about 24 centimeters per year. In the sediment at the bottom, researchers found a community of nematodes with a density 6 times higher than at the shallower edges of the same trench. In the southern hemisphere, while capitals and entire continents fill the map, the lowest point of the planet's southern half remains submerged and invisible to any direct human gaze. The Horizon Deep doesn't appear in any conventional atlas. It has no nearby city to serve as a reference point, no monument, no marker. Its existence is measured by instruments, inferred by sonar, and confirmed by scientific expeditions that rarely make the front page. The Horizon Deep, in the Tonga Trench, sits at 10,882 meters in depth, making it the second deepest point in the world's oceans. What makes the Tonga Trench unique isn't just its depth, it's the speed. To understand subduction, picture two enormous rigid slabs sliding beneath each other in extreme slow motion. In most subduction zones around the world, that movement happens at a few centimeters per year, comparable to how fast human fingernails grow. In Tonga, the process happens at a speed rarely documented in geology. The Pacific Plate dives beneath the Australian Plate at rates that, in the most active sections, reach 24 centimeters per year. Solid oceanic crust is permanently disappearing at that pace. That accelerated dive has consequences that go far beyond the ocean floor. Every centimeter of displacement builds up stress in the surrounding rocks, stress that eventually finds sudden release in the form of earthquakes. The Tonga Trench is part of the Circum-Pacific subduction zones. It's the most active area of deep earthquakes in the world, and it's well known for frequently producing earthquakes well above magnitude 7. Tsunamis generated in this region cross the Pacific in a matter of hours, reaching distant coastlines with devastating force. The abyss isn't just a geographic feature. It's a geological machine in continuous operation. In the sediment that slowly settles at the bottom of this trench, researchers found dense and unexpected biological communities. Nematodes, microscopic cylindrical worms that inhabit marine sediments in virtually every aquatic environment, were recorded at horizon deep in concentrations 6 times higher than those found at the shallower edges of the same trench. That pattern flipped the expected logic. The more extreme the environment, the lower the biological density. In the Tonga Trench, the logic works in reverse. The explanation lies in the accumulation of organic matter. Particles sinking from the ocean surface, remnants of marine organisms, feces, plant fragments, travel kilometers through the water column before settling on the bottom. Along the way, some of it is consumed by organisms in intermediate layers. What reaches the hadal floor represents a small fraction of the original total. However, in the deepest trenches, the concave geometry of the depression acts like a funnel, concentrating sediments from a larger area than the surface directly above. The result is a disproportionate buildup of nutritious material, which explains the surprisingly high biological densities. Researchers collected more than 3,600 individual amphipods from 10 species using baited traps at 2 sites, at horizon deep at 10,800 meters, and on a slope directly above at 6,250 meters. The abundance of amphipods collected at 10,800 meters was about 7 times greater than at the shallower site. Amphipods are benthic crustaceans that feed on sunken organic matter. Their high density at the deepest point confirms that the trench concentrates nutrients rather than dispersing them. These organisms represent a key link in the food chains of the deep. The speed of subduction in Tonga also means that the ocean floor in this region is geologically relatively young. Crust created at mid-ocean ridges, underwater mountain ranges where new ocean floor rises from Earth's mantle, travels for millions of years before reaching subduction zones where it's consumed. In Tonga, that cycle happens faster than in any other documented trench, creating a dynamic environment where the very bedrock has a more compressed geological history than in other regions. Investigating the Tonga Trench presents considerable logistical challenges. Its location in the South Pacific, far from major scientific centers in the Northern Hemisphere, limits how often expeditions can take place. Submersibles capable of reaching 10,800 meters exist in extremely small numbers worldwide. Each mission requires extensive preparation, specialized support vessels, and multidisciplinary teams. The cost and logistical complexity make each descent a once-in-decades scientific event, not an annual routine. Horizon Deep remains one of the least visited places on the planet. While Challenger Deep received significant media attention, following the expeditions of Cameron and Vescovo, the deepest trench in the southern hemisphere stays on the margins of public interest. Scientists who study it do so from a distance, through acoustic data, sediment samples collected by robotic vehicles, and inferences based on geological models. The deepest abyss in the southern world holds secrets that current technology is only beginning to decode. Each piece of data obtained rewriting what was thought to be known about the habitable limits of the planet. The Philippine Trench, also known as the Mindanao Trench, runs along the eastern edge of the Philippine archipelago for 1,320 kilometers. Its deepest point, the Galathea Deep or Emden Deep, reaches 10,540 meters. The site is named after the German research vessel SMS Emden, which first sounded the feature during an expedition in 1927, and alternatively after the Danish ship Galathea, which carried out detailed explorations in 1951. It was during that 1951 expedition that science discovered something it had considered unlikely. The Danish Galathea expedition retrieved live animals from several phyla at a depth exceeding 10,000 meters in the Philippine Trench, more than 2,000 meters below any previously known occurrences. Until that moment, it was believed that life could not exist below 8,000 meters. In 1927, a German warship called the SMS Emden was crossing the Pacific when its sounding instruments recorded an extraordinary depth off the eastern coast of the Philippines. There were no submersibles available to investigate. Only cables with weights were lowered to the bottom, measuring distance by the length of line needed to touch the ocean floor. That initial sounding noted a remarkable figure and gave the abyss its name. Originally discovered by the German ship Emden in 1927, the area was first explored in detail by the Danish ship Galathea in 1951 during the Galathea II expedition. The double name, Emden Deep and Galathea Deep, reflects two expeditions that, together, defined what science knows about this abyss. The German discovery recorded the existence of the depth. The Danish expedition, 24 years later, revealed what was inside it. The biological samples collected during the Danish expedition demonstrated for the first time that a wide variety of fish, amphipods, echinoderms, and bacteria not only survived but thrived in the deepest parts of the ocean. That discovery rewrote an entire chapter of marine biology. To grasp the impact of what the Galathea expedition found, you have to understand what was believed before 1951. The dominant hypothesis among oceanographers of the time held that below approximately 8,000 meters, what we now call the Hadal Zone, conditions would be incompatible with any form of metazoan life. Excessive pressure would destroy cell membranes. The absence of sunlight would eliminate primary production. Temperatures near zero and absolute darkness would make for a sterile environment. It seemed reasonable. It was wrong. The Philippine Trench stretches 1,320 kilometers parallel to the eastern coast of the Philippine archipelago, a scar on the ocean floor that runs along the edge of the tectonic plate where the Pacific Plate dives beneath the Philippine Plate. That collision simultaneously created both the trench and the archipelago itself. As oceanic crust sinks, molten material rises elsewhere, forming volcanic islands. The mountains that Filipinos call home and the trench that lies off their coasts are products of the same geological process, opposite sides of the same tectonic boundary. The creatures found by the Galathea expedition at over 10,000 meters included representatives of animal groups that science had only known from much shallower depths. Echinoderms, the phylum that includes starfish, sea urchins, and sea cucumbers, were recorded. Amphipods, highly adaptable crustaceans, were present. Diverse bacteria inhabited the sediments. Each group represented a lineage that had colonized the deep through independent evolutionary paths, developing specific adaptations to that extreme environment over immense geological periods. At the time of the expedition, the Philippine Trench was considered the deepest part of the ocean, a distinction it held until more refined measurements confirmed that both the Mariana Trench and the Tonga Trench surpass it. However, having once been considered the deepest point in the world focused significant scientific attention on it during the 1920s and 1950s. That focus produced detailed data that allowed later generations of researchers to compare the three great abysses of the Western Pacific. The first crewed descent to the Emden Deep was carried out by American underwater explorer Victor Vescovo and Filipino oceanographer Deo Florence Onda on March 23, 2021. Nearly 7 decades separated the discovery from the first human visit to the bottom. Vescovo brought a fellow Filipino along, a symbolic gesture, given that the trench runs along the coasts of the archipelago that bears its name. The findings from that expedition included, once again, human-made debris near the ocean floor. The presence of trash in the depths of the Philippine Trench repeats a pattern documented at Challenger Deep and other ocean trenches. Synthetic materials, plastics, processed metals, industrial compounds, accumulate at the bottom of abysses that should be the most isolated environments on the planet. These materials sink slowly, eventually settling in depressions where bottom currents concentrate them. Organisms that inhabit those sediments ingest microplastics alongside nutritious organic matter, incorporating artificial substances into food webs that have existed far longer than any human civilization. The hadal fauna of the Philippine Trench holds relevant biogeographic particularities. Each major trench in the Pacific, Mariana, Tonga, Philippines, functions like an isolated island in the deep ocean. The distance between them, combined with the difficulty of dispersal at extreme depths, encourages the development of endemic species. Researchers comparing biological samples from the 3 trenches find partial species overlap, but also forms exclusive to each location, the result of prolonged geographic isolation that shaped distinct lineages from common ancestors. 3 trenches, 3 abysses that challenge the human sense of scale in different but converging ways. The deepest point on the planet, the deepest in the southern hemisphere, the 3rd deepest in the world, all in the Western Pacific, all the result of the same plate dynamics that raised islands, generated earthquakes, and created habitats where life found ways to exist that no theory had predicted. The ocean floor that formed them continues its movement, imperceptible to any human observer, slowly deepening what is already deep beyond intuition, and holding, in the sediments accumulated over ages, records of a planet that existed long before any eye was here to witness it. The Kuril-Kamchatka Trench, off the coast of Russia and Japan, reaches a maximum depth of approximately 10,542 meters, almost identical to the Philippine Trench, and carries a seismic track record that none of the other top 5 deepest trenches can match in scale. The Kuril-Kamchatka Arc is one of the most seismically active regions in the world. The subduction zone is associated with at least 2 earthquakes of approximately magnitude 9.0 in the pre-instrumental period, in 1737 and 1841. The 1737 earthquake measured MW 9.0 to 9.3 and generated the largest known tsunami on the peninsula, 60 meters high. In July 2025, a magnitude 8.8 earthquake struck the region, generating waves of 5 to 7 meters along the coast. The same trench that forms one of the 5 deepest points on the planet produces some of the most destructive earthquakes and tsunamis in recorded history. Depth and geological violence rarely coexist in the same structure with such intensity. The Kuril-Kamchatka Trench is simultaneously one of the deepest ocean depressions on the planet and one of the most dangerous seismic zones in existence. To understand why, you have to picture what happens at the contact point between the Pacific Plate and the Okhotsk Plate, which occurs precisely there. The subduction of the Pacific Plate beneath the North American Plate has been ongoing since the Cretaceous period, at an estimated convergence rate of 76 to 90 millimeters per year. Every millimeter builds up stress that, when released abruptly, generates earthquakes of a scale rarely reached anywhere else on Earth. The subduction zone is associated with at least 2 known earthquakes of approximately magnitude 9.0 in the pre-instrumental period, in 1737 and in 1841. The 1737 earthquake measured between MW 9.0 and 9.3 and generated the largest known tsunami on the peninsula at 60 meters high, 60 meters of water wall advancing on the coast. To put that in perspective, a 20-story residential building stands approximately 60 meters tall. The 1737 tsunami raised a column of water the height of that entire building and hurled it against everything that existed along the Kamchatka coast. The deformation of the coastline was so drastic that native inhabitants could not recognize their own region after the waters receded. Centuries later, the same trench showed that its destructive potential hadn't diminished. The 2025 earthquake generated a tsunami with waves of up to 5 meters in Severokurilsk. The Shirshov Institute of Oceanology suggested the waves may have reached 10 to 15 meters along uninhabited stretches of coast. Compared to the 1737 event, the 2025 tsunami was considerably smaller, but that comparison, far from being reassuring, reveals just how much energy the subduction zone is capable of releasing when geological conditions align for a maximum rupture. The trench isn't spent, it's loaded. The mechanism behind this seismic violence is the same one that deepened the trench over millions of years. When the Pacific Plate dives beneath the Okhotsk Plate, the two rocky surfaces don't slide smoothly past each other, they lock. The friction between them builds up elastic deformation in the surrounding rocks, comparable to progressively bending a piece of metal until it reaches the limit of its resistance. When the stress exceeds the strength of the lock, rupture occurs in seconds. Hundreds of kilometers of tectonic interface shift simultaneously, converting decades of buildup into seconds of catastrophic release. The rupture zone of the 2025 earthquake was estimated at 700 kilometers long by 150 to 200 kilometers wide, with seismic displacement occurring at depths of 40 to 80 kilometers. Picture a fault surface larger than many entire European countries suddenly shifting. The energy released in that process propagates through the ocean as an elastic pulse, pushing the water column above it and generating waves that travel across the Pacific for hours before hitting distant coastlines. Beyond the earthquakes, the region has another indicator of its geological intensity: volcanoes. The Kamchatka Peninsula is one of the most volcanically active regions on the planet, with around 300 volcanoes, 29 of which are still active. Klyachevskaya Sopka is the largest active volcano in the Northern Hemisphere. Volcanoes and earthquakes in the same region are no coincidence. Both result from the same process. The subducted plate releases water and minerals as it melts in the depths, lowering the melting point of the mantle above it and generating magma that feeds the volcanoes at the surface. The depth of the trench, 10,542 meters, also results directly from the subduction rate. Older plates are denser and colder, diving at a steeper angle and creating deeper depressions. The Pacific Plate in this region has accumulated enough age to guarantee high density, favoring a pronounced descent angle. The resulting geometry creates an elongated V-shaped depression. The trench, whose walls record, in layers of sediment and deformed rock, a geological history of continuous collisions that far predates any human record. Studying the Kuril-Kamchatka Trench presents severe logistical difficulties. The region is remote. The Kamchatka Peninsula has limited overland access. Helicopters are the primary means of transportation, and weather conditions in the North Pacific impose considerable constraints on expeditions. Despite this, scientists have documented hadal fauna adapted to the trench's extreme conditions. Amphipods, polychaetes, foraminifera, and bacteria that thrive under pressure equivalent to 100 times what operational military submarines experience. The seismic history of the region redefines the concept of accumulated geological risk. An even larger earthquake may have occurred in 1737, with an estimated magnitude of up to 9.3 MW, based on historical records and tsunami deposits, including accounts of a 63-meter-high tsunami. That event, which took place almost 3 centuries before modern instruments, was reconstructed from geological deposits. Layers of sediment carried by the tsunami, driftwood found above the coastal line, accounts from explorers who visited the region years later and found the landscape unrecognizable. Geology preserves what no camera ever recorded. The Kuril-Kamchatka Trench stands as a living record that the planet is not at rest. The crust that appears solid and permanent is in continuous motion, trading stress for rupture in cycles that repeat regardless of any human presence on the surface. The most seismic trench among the 5 deepest in the world is no anomaly. It's a demonstration of the mechanism that created all of them, operating here with a peculiarly visible intensity for anyone monitoring the right instruments at the right moment, waiting for the next displacement already building in the locked rocks down below. The Kermadec Trench sits in the South Pacific, northeast of New Zealand, with a maximum depth of 10,047 meters. It's a direct continuation of the Tonga Trench to the north. Together they form a subduction system 2,000 kilometers long. In May 2014, the robotic vehicle Nereus, from the Woods Hole Oceanographic Institution, imploded in this trench at 9,990 meters of depth. Pieces of debris floating on the surface confirm that Nereus suffered a catastrophic implosion, with the intense pressure of more than 10 kilometers of water as the likely cause. A species of pearlfish, Echidon neotes, was caught in the Kermadec Trench at a depth of 8,200 to 8,300 meters. All other known pearlfish live between 1,800 and 2,000 meters, and the presence of this species at that depth remains unexplained. All 5 deepest points on the planet are in the Pacific. All are subduction trenches, scars where one tectonic plate dives beneath another, dragging the ocean floor into the depths. Implosion is the opposite of explosion. In an explosion, internal pressure overcomes the surrounding environment, and the structure violently expands outward. In an implosion, crushing external pressure overcomes internal resistance, and the structure instantly collapses inward. In the case of Nereus, a $5 million robotic vehicle built over years by the Woods Hole Institution, the implosion converted a sophisticated machine into a debris field in fractions of a second. Scientists say part of the vehicle likely imploded under pressure of up to 16,000 psi, pounds per square inch. For reference, truck tires operate at around 100 psi. The trench multiplied that pressure by 160. On May 10, 2014, at 2 p.m. local time, the hybrid vehicle Nereus was confirmed lost at 9,990 meters of depth in the Kermadec Trench, northeast of New Zealand. The unmanned vehicle had been on a mission exploring the hadal zone between 6,000 and nearly 11,000 meters of depth. The crew aboard the ship Thompson lost contact 7 hours into a dive planned to last 9 hours. When recovery protocols failed, a surface search began, and the debris found floating confirmed the worst. Preliminary investigations suggested that parts of the vehicle designed to maintain internal atmospheric pressure may have failed. Nereus was designed to operate in 2 modes: autonomous, mapping large areas without a surface connection, and remotely controlled via fiber optic cable. That versatility made it unique among deep-sea research vehicles of its time, capable of going where others couldn't. Its loss in the Kermadec Trench ended an exploration program and led engineers to fundamentally rethink the materials and architectures needed to survive pressures at that level. The Kermadec Trench and the Tonga Trench to the north form a single continuous tectonic system. The Kermadec Trench runs from northeast of New Zealand's North Island to the Louisville Seamount Chain, formed by the subduction process where the Pacific tectonic plate is pushed beneath the Indo-Australian plate. This 2,000-kilometer system represents one of the longest and most active plate boundaries in the South Pacific, and the trench that marks it is, from a biological standpoint, territory of discoveries that continue to surprise. The case of the pearlfish caught at 8,200 meters is one of the most intriguing puzzles in hadal biology. Echidon neotes belongs to a family that, in every other documented record worldwide, lives exclusively between 1,800 and 2,000 meters. Finding it at more than 4 times that depth suggests either the accidental dispersal of a lone individual or a population unusually adapted to pressures that no known member of its family should be able to tolerate. Neither hypothesis has been ruled out. Neither has been confirmed with sufficient data. Discoveries like this reveal that the hadal zone, below 6,000 meters, is not a defined biological boundary, but a gradient that different lineages cross through specific adaptations that are still only partially understood. The pressure that destroyed Nereus doesn't stop adequately adapted biological organisms from thriving. The difference between the machine and the living creature lies in how each deals with the pressure differential between inside and outside. Machines try to maintain low internal pressure, creating a gradient that external pressure can collapse. Hadal organisms equalize their internal pressure with the environment, eliminating the destructive gradient. The implosion of Nereus also raised urgent practical questions for deep-sea exploration engineering. Nereus had been built in 2008 with primary funding from the U.S. National Science Foundation. It was capable of descending to the deepest parts of the ocean and operating both autonomously and by remote control from the surface. It was one of the few vehicles in the world with that capability. Its loss created a gap in the tools available for hadal research at a time when scientific interest in ocean trenches was growing. Replacing it required years of redesign and testing. The Kermadec Trench also holds sediments that accumulate records of regional geological events over millennia. Volcanic eruptions from nearby islands deposit identifiable ash layers. Tsunamis generated by earthquakes leave strata of disturbed sediment. Debris flows from New Zealand's islands bring organic matter that feeds benthic communities. Each layer is an archive of a specific event, datable by geochemical methods, which allows the environmental history of the region to be reconstructed with increasing precision as analytical methods advance. The presence of this trench so close to New Zealand, a country with a small population but a relevant tradition of ocean science, has allowed more frequent access than other Pacific trenches. New Zealand and Australian research vessels have carried out regular expeditions, building a comparatively rich dataset on its biology, geology, and chemistry. Even so, given the cost and operational difficulty, each dive to depths near 10,000 meters remains a significant scientific event, planned months in advance, executed with minimal margins for error, and capable of revealing specimens and processes that no theoretical model had predicted. The distribution is no coincidence. The Pacific is the oldest, deepest ocean and the one most surrounded by active subduction zones. The Ring of Fire, which contains 75% of Earth's active volcanoes and 90% of the largest recorded earthquakes, defines its edges. The Pacific Ring of Fire is about 40,000 kilometers long in a horseshoe shape. Each of the 5 deepest trenches on the planet exists because one tectonic plate is being pushed beneath another along that ring, creating V-shaped scars on the ocean floor that concentrate sediment, organic matter, and eventually the entire oceanic crust, which disappears into Earth's mantle. The Tonga Trench swallows crust at 24 centimeters per year. The Kuril-Kamchatka Trench builds up stress that it releases in magnitude 9 earthquakes. The Kermadec Trench imploded a robot at 9,990 meters. The Philippine Trench is where science first discovered life below 10,000 meters. And the Mariana Trench holds the deepest point on the planet, where plastic and candy wrappers have already been found. 5 trenches, 5 records, 1 ocean. The concentration is no geographic accident. It's the consequence of a specific geological architecture that makes the Pacific the most violent, deepest, and most active ocean on the planet. The Ring of Fire runs approximately 40,000 kilometers, following island arcs like Tonga and the New Hebrides, the Indonesian archipelago, the Philippines, Japan, the Kuril Islands, and the Aleutians, as well as arc-shaped geomorphological features like the western coast of North America and the Andes. Every stretch of that ring marks a point where one plate is disappearing beneath another, and where the ocean floor sinks. The Ring of Fire generates approximately 90% of all earthquakes on the planet and concentrates 75% of active volcanoes. A chain of 452 volcanoes stretches from the southern tip of South America, runs up along the North American coast, crosses the Bering Strait, runs down through Japan, and reaches New Zealand. That inventory isn't a list of curiosities. It's a description of a planetary system in active operation. The earthquakes and eruptions that make headlines with unsettling regularity are surface manifestations of processes occurring tens of kilometers underground, where plates lock and slip on geological timescales. The Pacific is also the oldest ocean. Its oldest oceanic crust is approximately 200 million years old, a period so far before the appearance of the first dinosaurs that any analogy with human timelines immediately falls apart. Over that time, the crust was produced at mid-ocean ridges, slowly drifting toward the ocean's margins and eventually diving into subduction zones. The older the crust, the denser and colder it is, and the more steeply it dives, creating deeper trenches. The Pacific has old enough crust to produce the 5 deepest depressions that exist. Each of the 5 trenches is, at its core, the same geological process operating in slightly different contexts. In Tonga, the record subduction rate creates the deepest trench in the southern hemisphere. In the Kurils-Kamchatka, the size of the plate contact interface concentrates enough seismic energy for 60-meter tsunamis. In the Philippines, the history of collisions between plates of different ages created the environment where the 1951 Galathea expedition found life where science was certain none existed. In Kermadec, pressure destroyed sophisticated engineering, while biological organisms thrived just meters below the wreckage. In the Mariana Trench, the deepest point on the planet accumulates both geological records spanning ages and plastic from candy wrappers produced 11 kilometers above. The sequence of 5 records reveals a pattern that isolated statistics don't capture. The depth differences between them are smaller than most people would expect. Between the deepest, Mariana, at 10,984 meters, and the 5th, Kermadec, at 10,047 meters, the gap is 937 meters. Less than 1 kilometer separates the all-time record from 5th place, on a planet with a radius of 6,371 kilometers. All 5 were created by the same mechanism, operate under the same physical laws, and present conditions that make direct human exploration technically extreme in every case, not just the absolute record holder. The biology of the trenches also converges on common patterns, despite the geographic distances. Research in the Tonga Trench found that several amphipod species on record are shared with other Pacific trenches, suggesting that the fauna of the New Hebrides, Tonga, and Kermadec trenches may represent a single biogeographic province. Species capable of dispersing eggs or larvae across the deep ocean have colonized multiple trenches over geological timescales. Other lineages became isolated, generating endemic forms found in only one trench, invisible biodiversity that science is still cataloging. The concentration of all 5 trenches in the Pacific also means a concentration of human risk. The coasts of Japan, the Philippines, Indonesia, New Zealand, and Chile, countries with significant coastal populations, are directly exposed to tsunamis generated in these subduction zones. The Ring of Fire was the stage for some of the largest earthquakes in recorded history, including the 1960 Chile earthquake, the 1964 Alaska earthquake, the 2010 Chile earthquake, and the 2011 Japan earthquake, as well as the earthquake that produced the devastating 2004 Indian Ocean tsunami. Each of those events originated from a subduction trench, the same type of structure that creates the deepest points on the planet. Ironically, the ocean trenches that represent the most hostile environments on the planet for any human exploration are also the best geological archives available. Sediments that settle at 10,000 meters of depth are protected from disturbances that affect shallow ocean floors, currents, biological activity from larger organisms, physical impacts. The stratigraphic record at the bottom of the trenches preserves climate events, volcanic eruptions, variations in ocean productivity, and pulses of land-derived sediment with a resolution that shallow water samples rarely offer. The most inaccessible abyss is also the most intact archive. The Ring of Fire didn't choose the Pacific out of arbitrary geological preference. The Pacific created the conditions for the Ring of Fire. It's the ocean most surrounded by thick, less dense continental plates, ensuring that oceanic crust always ends up diving beneath them at the margins. It's the largest ocean on the planet, accumulating crust old and dense enough to plunge at a steep angle wherever it meets resistance. It's the most tectonically isolated ocean, without the complexity of direct continental collisions that characterizes the Mediterranean and the North Atlantic. All of that converges to produce 5 trenches, 5 records, 1 ring of continuous geological violence. And down below, organisms that never knew the difference between the deepest and the second deepest, only that dark, cold, compressed place was somehow the right environment to exist in. If the pressure doesn't kill you, the heat might. Scattered across the ocean floor along mid-ocean ridges, hydrothermal vents expel superheated water at temperatures lethal to any organism that isn't adapted for it. Fluid temperatures can reach 400 degrees Celsius or more, but they don't boil under the extreme pressure of the deep ocean. At 400 degrees Celsius and the pressure corresponding to 3,000 meters of depth, water becomes a supercritical fluid, neither liquid nor gas, that dissolves metals and reacts chemically with any material it contacts. As it emerges from a vent, fluid at 400 degrees Celsius meets seawater at 2 degrees Celsius within a matter of centimeters. The temperature gradient across less than 1 meter is 398 degrees Celsius. No human biological system survives that gradient, but Pompeii worms and chemosynthetic bacteria live right at that boundary, proving that the definition of habitable depends entirely on who's trying to do the inhabiting. To understand why water doesn't boil at 400 degrees Celsius on the ocean floor, you have to understand what boiling actually is. Boiling occurs when the vapor pressure of a liquid exceeds the pressure of the surrounding environment. The molecules gain enough energy to escape the liquid phase and become gas. At high altitude, where atmospheric pressure is lower, water boils below 100 degrees Celsius. The inverse is also true. since mid-ocean ridges sit at depths of 2,000 to 4,000 meters, under pressures between 200 and 400 bar. Water can reach temperatures between 350 degrees Celsius and 400 degrees Celsius without boiling. The colossal pressure of the water column above suppresses the phase transition that under normal conditions would occur at 100 degrees Celsius. The resulting state, supercritical fluid, is neither conventional liquid nor steam, but something with properties of both simultaneously. Supercritical water diffuses like a gas, but maintains a density close to that of a liquid. In that state, its ability to dissolve minerals increases dramatically. The hydrothermal fluid, at temperatures of 300 to 400 degrees Celsius and low pH, returns to the ocean floor, leaching and transporting metals and other elements, which eventually precipitate as sulfide deposits on the ocean floor. The black smoker chimneys of hydrothermal vents are literally built from minerals that the water dissolved in the rocky depths and deposited as it emerged. The discovery of hydrothermal vents in 1977 revolutionized biology. Until then, every known food chain ultimately depended on solar energy. Plants fix sunlight, animals eat plants, other animals eat those animals. Hydrothermal vents demonstrated that complex life can exist with no relationship to solar energy whatsoever. To scientists' astonishment, the vents were surrounded by large numbers of organisms never seen before. A diverse ecosystem thrived there, even in the complete absence of sunlight, which had been thought to be essential. Chemosynthetic bacteria replace photosynthesis, extracting energy from chemical reactions between sulfides and oxygen. Hydrothermal vents were first discovered in 1977 at around 2,700 meters of depth in the Galapagos Sea. Temperatures can range from 40 degrees Celsius to 464 degrees Celsius, and the minimum and maximum depths on record range from 400 meters to 6,000 meters. The thermal range of these structures is remarkable. The difference between the minimum and maximum recorded temperatures within the system exceeds 420 degrees Celsius, a span that in any land-based context would stretch from refrigerator temperature to the industrial furnace used to smelt aluminum. The temperature gradient around hydrothermal vents creates distinct microenvironments on a scale of centimeters. Just a few centimeters from the active opening, temperature drops from 400 degrees Celsius to tens of degrees. Adapted organisms exploit precisely that gradient, positioning themselves in specific zones with the temperature and chemistry suited to their metabolism. Pompeii worms, Alvinella pompejana, are the most heat-tolerant animals ever documented, withstanding temperatures of up to 80 degrees Celsius on their backs while keeping their heads in cooler water. No other known metazoan life form survives in that thermal range. The chimneys formed by the abrupt cooling of hydrothermal fluids grow rapidly by geological standards. Upon meeting the low temperatures of ocean water, dissolved minerals are expelled and deposited around the vent opening, creating what are known as chimneys or smokers, which can reach 60 meters in height, growing 30 centimeters per day. 30 centimeters per day is an extraordinary speed for rock formation. Structures that would be classified as underwater mountains on a human scale emerge in months, where before there was only flat ocean floor. The ecosystems that thrive around hydrothermal vents include not just bacteria and worms, but organisms from multiple phyla. Specialized blind shrimp, adapted octopuses, fish that tolerate conditions no shallow water equivalent could handle. Each species occupies a specific niche in the temperature and chemistry gradient, forming a complete and self-sufficient food web. The biomass per square meter in these islands of heat and chemistry can far exceed that of any surrounding deep ocean environment, oases of life in abyssal deserts. The chemistry produced by hydrothermal vents also influences the composition of the global ocean. Dissolved minerals released into bottom currents travel thousands of kilometers before precipitating or being absorbed by organisms. That continuous flow of elements such as iron, manganese, zinc, and copper connects the ocean floor with the surface in ways that science is still mapping. The Pacific Ocean has the highest spreading rates at mid-ocean ridges, between 2.4 and 15 centimeters per year, resulting in a higher concentration of hydrothermal fields. The same ocean with the 5 deepest trenches is also the richest in active hydrothermal vents. The boundary between lethal and habitable at hydrothermal vents is not absolute. It's functional and dependent on specific adaptation. The fluid at 400 degrees Celsius that would dissolve any metal in minutes is, for the microbial communities inhabiting the chimney walls, simply the environment from which energy comes. The pressure that prevents boiling is the same pressure that keeps these ecosystems sealed and stable for decades. The 398 degrees Celsius gradient that would kill any human in fractions of a second is, for a Pompeii worm, simply the address where it lives, a demonstration that hostility is always a relative concept, and that the ocean, even at its most extreme points, has found ways to be home to something. Even before you dive in, the ocean presents its first threat right at the surface. Waves that appear without warning and reach twice the height of the surrounding swells. Rogue waves are unpredictable and can suddenly come from directions that don't match the prevailing wind or waves. Most witnesses describe them as walls of water because of their unusually deep troughs. Between 1969 and 1994, rogue waves were responsible for the complete sinking of 22 supertankers, often with their entire crews. The first instrumental measurement of a rogue wave was the Dropner wave, a 25.6-meter monster recorded in the North Sea on January 1, 1995. In February 1995, the cruise ship Queen Elizabeth II encountered a 29-meter rogue wave during a hurricane in the North Atlantic. The captain described it as a great wall of water. It looked like we were heading for the white cliffs of Dover. In December 2022, a rogue wave struck a cruise ship in the Antarctic Ocean, killing 1 passenger and injuring 4. A regular wave behaves predictably. Height, period, direction, parameters that meteorologists and captains monitor and plan for. Ships are designed to withstand the largest waves expected within a given statistical safety margin. By technical definition, a rogue wave has a height greater than twice the so-called significant wave height, the average of the highest third of waves present in a given area. The Dropner wave was recorded on January 1, 1995, with a maximum height of 25.6 meters. The significant wave height in the area was approximately 12 meters, meaning the Dropner wave was more than twice the size of the surrounding waves, with characteristics that didn't fit any known wave model. The platform that recorded the Dropner wave was a robust steel structure designed for extreme North Sea conditions. The Dropner platform was built to withstand a 64-foot wave, with a probability of occurring once in 10,000 years. The 1995 Dropner wave measured 85 feet, 21 feet taller than projected, and its characteristics didn't fit any prior wave model. A wave that statistically shouldn't appear for 10,000 years showed up before the platform had even finished its first decade of operation. That doesn't indicate a failure in the engineer's calculations. It indicates that the mathematical models available at the time were systematically underestimating the frequency of the phenomenon. The physical explanation is still debated among oceanographers. Several hypotheses have been proposed and tested since 1995. Waves traveling in different directions can interact in nonlinear ways, momentarily stacking their heights in ways that linear models don't capture. Strong ocean currents can compress the wavelength of swells moving against them, proportionally increasing their height. A recent study concluded that the phenomenon of nonlinear crest enhancement rather than energy concentration between waves, is the mechanism that pushes already violent seas into the catastrophic range. Understanding of the phenomenon is advancing, but the ability to predict exactly when and where a specific rogue wave will appear remains beyond current scientific reach. For historical navigation, rogue waves were sailors' legends. Accounts from surviving castaways or crews describing vertical walls of water were treated as exaggeration or trauma. Statoil scientists concluded in 2000 that, far from being an ultra-rare phenomenon, rogue waves were likely far more frequent than previous models had predicted. That was confirmed by satellite radar studies. Satellites equipped with synthetic aperture radar began recording anomalous waves across the global ocean, revealing that the phenomenon occurs at multiple locations in any given week. It's not a rarity, it's a recurring event that ships encounter far more often than was officially acknowledged for decades. The geographic distribution of rogue waves is not uniform. Regions where strong ocean currents meet winds and waves coming from the opposite direction are particularly prone to them. Cape Agulhas in South Africa, where the Agulhas current flows in the opposite direction from Antarctic ocean storms, has a history of rogue waves that have destroyed supertankers. The North Sea, where low-pressure systems generate waves that interact with shallow floors and complex currents, was the setting for both the Draupner wave and numerous accidents. The Antarctic Ocean, with the highest waves on the planet and no continental landmass to interrupt them, saw the fatal 2022 cruise ship incident. Offshore structures, oil and gas platforms installed in open water, represent the most detailed inventory of damage caused by anomalous waves. Radar data from the Goma oil field in the North Sea recorded 466 turbulent waves over 12 years, helping to convert previously skeptical scientists, whose statistics showed that deviations that large from the surrounding sea state should only occur once every 10,000 years. 466 events in 12 years versus one event in 10,000 years. The gap between the model and reality was several orders of magnitude. The documented history of rogue waves since 1995 includes examples with enough amplitude to submerge cargo ship decks, tear hatches off submarines, and project water against bridge windows at heights that no conventional ocean vessel design had ever considered relevant. Satellite monitoring networks now identify ocean anomalies in near real time. Data that reaches maritime weather centers and can be translated into alerts for shipping routes under specific conditions. It's not the individual prediction of each wave, but a mapping of the conditions that increase the likelihood of occurrence. What the Draupner wave definitively established was not just that rogue waves exist. It was that the oceans are capable of behaviors that models built on well-understood physics cannot predict with sufficient accuracy. That scientific humility has practical implications. Ships crossing the North Atlantic or the Antarctic Ocean today carry, on some percentage of any given voyage, the risk of encountering a water structure they were not specifically designed for. Naval engineering is advancing toward more resilient hulls and more sensitive monitoring systems. But the ocean remains capable of creating, in seconds, water heights that decades of calculations had considered impractical. In the zone where humans actually enter the ocean, the coastal surf zone, the primary threat has no teeth, no body, and no visible form. Rip currents are narrow channels of water that flow rapidly out to sea, perpendicular to the shore, capable of dragging any swimmer regardless of their skill level. An Olympic swimmer cannot swim against a rip current moving at 2.5 meters per second. The speed physically exceeds the maximum swimming speed of any human in any stroke. In the United States, rip currents are responsible for more than 80% of rescues performed by lifeguards on ocean beaches. Sharks killed 7 people worldwide in 2024. In 2024, there were only 47 unprovoked bite incidents in total, across all shark species, with 7 fatalities. Rip currents kill dozens of people every year in the United States alone. Invisible, shapeless, and without the reputation that sharks carry. The gap between the fear people feel toward sharks and the actual danger that rip currents represent is one of the most studied examples of risk misperception. Sharks are visible, have teeth, and star in movies and headlines. Rip currents are invisible, have no shape, and don't attack deliberately. They simply exist, and whoever swims into one gets pulled away. Every year, more than 100 beachgoers drown in the U.S. due to rip currents, according to the United States Life-Saving Association. Nearly half of all lifeguard rescues on ocean beaches worldwide are related to rip currents. 50% of all rescues, from a phenomenon with no common name, no mainstream cultural representation, and no prevention campaign anywhere near the recognition sharks receive. Understanding how a rip current forms requires picturing what happens to the water that waves continuously push toward the shore. Waves break in the surf zone, pushing large volumes of water toward the coast. That water has to go back out to sea. On beaches with uniform topography, the return happens in a diffuse way. Where the ocean floor has deeper channels, between sandbars near rocky structures, alongside jetties and groins, water finds the path of least resistance and funnels through that point. The result is a narrow, fast current running perpendicular to the shore that can reach speeds of 2 to 2.5 meters per second. An Olympic swimmer cannot swim against a rip current moving at 2.5 meters per second. Essentially, they are rivers in the sea, says Wendy Carey, a coastal hazards specialist with the Delaware Sea Grant Advisory Service. The river analogy is accurate. Trying to swim directly against the current is the equivalent of trying to swim upstream against a river. The energy spent exhausts the swimmer without moving them toward shore. The correct technique is to swim parallel to the beach until you exit the narrow channel of the current, then swim toward the sand. Most fatal victims don't know this technique, or they know it, but lose the composure needed to apply it while being dragged away. A common misconception is that rip currents pull swimmers underwater. In reality, they are strong, narrow currents that flow away from the shore. That confusion makes the risk worse. Swimmers who believe they're being pulled under tend to fight violently to get back to the surface, burning through their energy. Those who understand they're being carried horizontally out to sea have a better chance of staying calm, floating, and swimming sideways to escape. The difference between panic and knowledge is, in these cases, often the difference between surviving and not. The deceptive appearance of rip currents contributes to accidents. Rip currents above deep sandbar channels look like calm patches of water, often sitting between turbulent breaking waves, presenting what looks like an inviting path for inexperienced beachgoers. The calm area appears to be the safer spot to enter the water compared to the noisy surf zones on either side. That visual invitation is a trap. The surface calm is caused precisely by the intense outflow pulling water to sea, preventing waves from breaking at that point with normal intensity. A survey by the fire department indicates that 9 out of 10 drowning deaths occur in rip current areas. That figure puts rip currents in a radically different category from any other ocean threat in the coastal zone. Compared to sharks, which kill roughly 7 people globally per year, the numbers aren't even close. In Brazil, the São Paulo coastline records a significant number of rescues tied to this phenomenon, even on beaches frequented by experienced swimmers. The current doesn't discriminate based on physical fitness. Identifying a rip current before entering the water is a skill that can be learned. Attentive observers notice that the surface of a rip current often has a slightly different color, murkier, with sediment suspended in the flow. The absence of breaking waves in a specific stretch, while waves break normally on either side, is another sign. Foam or floating debris visibly moving out to sea also indicates a current. Trained lifeguards recognize these patterns and mark off hazard areas, but they aren't present at every beach at every hour. The correct response when caught in a rip current is counterintuitive enough to fail under the pressure of panic. Don't fight the current, don't swim toward the beach, don't try to sink to escape along the bottom, but swim parallel to the shore, conserving energy until the current dissipates. Rip currents generally end beyond the surf zone, spreading out once they no longer have lateral confinement. Swimmers who stay calm and follow the correct technique can escape with energy to spare. Swimmers who panic and fight head-on against the current exhaust themselves, go under, and become part of a statistic that most of the public mistakenly attributes to other causes. The ocean that appears safest, the shallow coastal strip, waist-deep water, small waves, a beach packed with families on a sunny day, is precisely the environment where rip currents kill the most people. Not deep-sea divers, not surfers riding big waves, not fishermen offshore, but regular beachgoers who waded into what looked like a calm stretch of an ordinary beach, in conditions no weather forecast would flag as dangerous, and were carried away by the invisible river that no ocean hazard story tends to mention, while the summer news cycle keeps running stories about sharks spotted offshore. On the same day, that beach was the site of rescues from currents nobody saw until it was too late. The ocean covers 361 million square kilometers. At any point in that territory, an unprotected human has a survival window ranging from minutes to hours before hypothermia, pressure, drowning, or chemical poisoning ends the process. Pressure destroys submersibles in milliseconds at 3,800 meters. The bottom has water at 400 degrees Celsius that doesn't boil. Dead zones expand without warning. Tsunamis invisible in the open ocean turn into 30-meter walls at the coast. Rogue waves of 29 meters appear without forecast. Rip currents exceed the maximum speed of any human swimmer, and 74% of the floor of this environment has never been mapped in high resolution. The same ocean that destroyed OceanGate's Titan in milliseconds, that has superheated water at 400 degrees Celsius on the floor, that already has plastic waste scattered across the most inaccessible points on the planet. That ocean absorbs 25% of human CO2, regulates the climate of every continent, sustains the largest food chain on the planet, and is the reason Earth's atmosphere still has enough oxygen to breathe. The planet's ultimate threat is also its life support system. Laying out all the ocean's dangers in sequence reveals a pattern that no isolated data point can convey with the same clarity. Each layer of the ocean, from the surface to the deepest trenches, offers a different mechanism of destruction. At the surface, rogue waves and rip currents. Below the surface, hypothermia and drowning. Deeper still, crushing pressure and absolute darkness. At the bottom of the trenches, pressure of 1,000 atmospheres and temperatures near zero. Along the mid-ocean ridges, water at 400 degrees Celsius. Each zone has its own rules, and none of them were set up to accommodate unprotected human existence. The ocean absorbed 93% of the heat accumulated in the atmosphere due to the enhanced greenhouse effect, and captured more than a quarter of anthropogenic CO2 emissions since 1750. That figure, a quarter of all the carbon dioxide that industrial civilization has emitted since the Industrial Revolution, represents absorption on a scale that no artificial system ever created by humans comes anywhere close to replicating. Without that oceanic sink, the concentration of CO2 in the atmosphere would be considerably higher than it is today, and the climate consequences already underway would be even more severe. Phytoplankton produces between 50% and 80% of atmospheric oxygen, a volume that surpasses the contribution of all land forests combined. The oxygen any human being is breathing right now has more than a 50% chance of having been produced by microscopic organisms floating in the first 200 meters of depth of of the world's oceans. Not tropical rainforests, not trees, not land plants, but single-celled algae so small that dozens of them fit in a millimeter, performing photosynthesis at industrial scale distributed across 361 million square kilometers of ocean surface. The ocean is a fundamental player because it has contributed significantly to softening the scale of contemporary climate change, absorbing 93% of the heat accumulated in the atmosphere. That heat doesn't disappear. It warms ocean waters, altering current circulation, species distribution, hurricane patterns, and polar ice volumes. The ocean pays a real price for absorbing the atmosphere's excesses: acidification, warming, expansion of hypoxic zones. The same buffering capacity that protects the climate benefits civilization at the cost of the system that makes it possible. The oceans are natural carbon sinks that absorb around 25 to 30% of all CO2 emissions from the atmosphere, more than forests, playing a crucial role in the fight against climate change. Tropical forests, frequently cited as the lungs of the planet, contribute a smaller fraction than total global oceanic carbon absorption. That hierarchy matters for any honest understanding of how the terrestrial biosphere works, and which elements, if disrupted, would carry the broadest consequences. The food chain that starts with phytoplankton sustains everything that exists in the ocean. Zooplankton that eats phytoplankton, small fish that eat zooplankton, larger fish that eat those, and so on up to the species at the top of marine food chains. That chain also feeds human populations. Approximately 3.3 billion people depend on seafood as their primary source of animal protein. The ocean that kills any unprotected human within its domain simultaneously sustains more than a third of the human population as an essential source of nutrition. The fundamental irony is that the same environment that accumulates plastic waste from the surface all the way to the bottom of the deepest trenches is the system that keeps the atmosphere breathable. Plastic found in Challenger Deep, in the Tonga Trench, in the Philippine Trench, materials produced at the surface that travel kilometers through the water column to contaminate the planet's most intact archive, reveal that human disruption of the ocean respects neither distance nor depth. The ocean that built the atmosphere over billions of years through phytoplankton is being altered by a species that depends on it to breathe, whose industrial metabolism produces exactly the excess CO2 that the ocean tries to absorb in order to maintain the balance that made the existence of that same species possible. In just 6 years, phytoplankton is capable of completely renewing the volume of gases exchanged between the ocean's light layer and the atmosphere, a silent, invisible, and absolutely essential cycle. 6 years. The time it takes to travel the distance between Earth and Jupiter aboard a hypothetical spacecraft is the same time the ocean takes to completely renew its gas exchange with the atmosphere. The system that would seem most static, a vast and apparently motionless ocean, operates on cycles of continuous renewal, invisible to direct human perception, but measurable and fundamental. The narrative of the ocean as threat finds, in that 6-year cycle, its counterpoint. The most efficient adversary that human biology can face is also the most essential mechanism the terrestrial biosphere has for maintaining the conditions that made possible any form of life capable of studying, fearing, and ultimately damaging the ocean that has sustained it from the very beginning.